Hello and welcome to day 3 of Advent of Code in F#. Let's fly right into it. Oh, I see maps again. With the toboggan login problems resolved, yay! You set off towards the airport. While travel by toboggan might be easy, it's certainly not safe. There's minimal steering, yeah. Due to the geology, trees in this area only grow on exact integer coordinates in the grid. That's useful for programmers. We get a map, our input of the open squares and trees. So cool. So there's trees, yeah. Those aren't the only trees. Due to something we read about once involving arboreal genetics and biome stability. The same pattern repeats to the right. Only to the right. Interesting. So we have a never-ending forest. Start in the open square in the top left. Cool. So coordinate-wise, that's interesting as well. We need to reach the bottom. Below the bottommost row. Okay, we need to drop out of the map. Toboggan can only follow a few specific slopes. Interesting. A cheaper model that prefers rational numbers. Also another programmer's dream. Start by counting all the trees you would encounter. Okay, we need to count trees we encounter. For slope, right 3, down 0, down 1. Okay. We start on top left and we go right 3, down 1 in steps. Yeah. 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, and we count how many trees we hit in this ever-growing forest until we drop out. Okay, that's clear. Interesting. Okay, the X's are trees, the O's are misses. For our puzzle input, how many trees would we encounter? Alright. Oh, that's a big forest. Okay, interesting. So let me just put it in a buffer somewhere. 323 lines of tree. Oh boy. Do we need to read it by lines? Yeah. So let's load it in. There we go. This is a bigger problem. I think we're gonna need to cut it down into several pieces, several steps. So what do we need to do? We need to parse the map. I think I'm gonna keep it with a 2-dimensional array. Yeah, and handle the infinitely growing forest thing just by when we access the matrix or the 2-dimensional array, just like looping around when it needs to. We need to like have movement, so we need to keep track of where we are and how many trees we've been hitting. And there's no... Is there a fixed amount of steps? Yeah, actually there is a fixed amount of steps to drop out. It's a single fixed pattern, right 3, down 1. So down 1 means we drop 1 row down. So in theory we could do it in a fixed number, or no, it'll always be a fixed number of steps. So for us it would be 323. How many lines did we have? Yeah, so in 300 steps. I'm thinking, should we do it that way? Or I'm thinking ahead, maybe that's a bad idea, but in part 2 maybe there's a different pattern and we will go down faster, or we'll go back up and it'll be crazier. So I think I'm gonna go for a different approach. I'm gonna not have a specific set of steps. I'm just gonna keep moving, keep taking a step using the pattern until we drop out. So like a while true kind of thing you do in C#. Yeah, okay, so let's start with the first problem first. Let's parse our forest. Okay, so we have a list of strings, an array of strings. Yeah, it's an array. Whenever I do these kinds of mazes things or are parsing a grid, I like to put some types around it, so let's do that as well today. So we have a forest, which is like the collection, and we have spaces that have a tree or don't have a tree. How would we represent that fact? Record type. I'm thinking of a name. A space. It's not the best word, but can't think of anything better. So space either has a tree or is empty. So the forest is a grid of spaces. Let's define a parser. Forest. So this should build our map. So we need to read all those lines, and then we need to read all the spaces in a line and form a two-dimensional grid. Okay, if we loop over the lines and then loop over every element and parse that into a space, that'll work. So what are we returning? We are returning a list or an array. Doesn't make that much difference, I guess. Now let's keep it a list. So for every row in our input forest, forest is a bad name, let's call it lines, yeah. Row, so this doesn't do much except return our list again. Okay, so now we're working on a row. And for a row we need to return a list of spaces. So for space in a row, we return that's the character. Wait, let's type this. Sequence of something, yeah, and here's a string array. So let's make this a sequence of strings. So this is now a character. There we go. And let's parse. Let's just write inline here, match as with. We can have dot, which would mean empty, and we can have a hash, or how do they call it? Let's go, I'm gonna call it a hash for the remainder of this session, and call it a tree. Was it? Oh, sorry. So there's a bit of a trick with for expressions when you use the arrow syntax, when you use the do syntax, but compiler is pretty handy in this case. And let's just do a catch-all. If we find something wrong, we're just gonna crash. That's not what he was saying. What's it saying? It's implicitly ignored. Oh yeah, interesting. So actually, there's a yield keyword that allows you to return things, but I think the arrow syntax is the same as a do yield. So I'm not sure why this is failing, because there has to be a do here. Yeah. Okay. There's only one problem with the thing I'm building right now. It takes our input, that's correct, but it's returning a flat list. So we need to nest this again. And that's where we have to have a nested list. Now I'm flying on improvisation. I don't know the exact syntax or the exact F# syntax to build a nested list. using 4 comprehensions. Is this what we want? A list of spaces? Yeah, I think so. I'm feeling uncomfortable, so let's test it a bit. Our parser. Yeah, let's define a test grid. So what was the thing? A string sequence. So we just need a list of strings. And when we parse that, well, let's make a 2 by 2 grid. Something like this, and then something like this. So a 2 by 2 grid, and let's try to parse that. Parse test grid. Come on, give us an error. There we go. So when we parse this thing, it's empty tree. Okay, this is leaking a bit of the implementation details, because now this test is saying, oh sorry, this is what I was trying to do. Trying to inline this and then inline this. What am I trying to say? If I was writing production code, this is a bit dangerous, because now we're leaking the structure of our parsers, the return type of our parser. We're leaking its internal structure, like it's a list of states. So whenever that changes, this thing will change as well. What am I trying to say? That in production I would use something called abstract data types. So something like a forest type, and you would have functions that work on this forest type, and instead of functions that work on lists of spaces, so that the rest of the code is not impacted that much when structure changes happen. But this is a quick puzzle. We know what we have to achieve, so let's go with this for a while. But our parser seems to be working. The final check, or the ultimate check, is parsing our input, so let's try that. Let's parse our input. Let's see what we get. We get a whole lot of empties, trees. So I'm going with probably okay. Next step, finding our way in the map. So whenever we're at the location, we would like to know, are we hitting a tree or not, basically. Now I'm hoping that lists have the same index access structure things as arrays, so I'm gonna quickly test that out. We have a list. Can we access it by index? Yeah, we can. Okay, so this will work. So let's write a function that, given the forest, like our data structure containing the spaces, that tells us that at a given location, a specific coordinate, whether or not there's a tree. So I'm gonna call it tree add. Yeah, why not? Tree add. No, tree add is maybe not enough. I'm gonna call it element add, because maybe I'm gonna use this for, is there a tree or not, and at the second case, have we fallen out of the grid or out of the forest. So element add a forest and a location. So first let's try to look up the space at that location. So forest, and this is where we're gonna dig into the data structure we return from the parser. So it's a list of spaces. You know what? I'm gonna type it explicitly. Space list. So we get it's not a tree, it's a forest. Go. So when we do element add, we get a forest, and we have a location. I don't think we're gonna evolve to a 3D thing, so let's call it. Let's work with a tuple representing an x and a y coordinate, and maybe let's quickly draw our grid. or no, we have this example. So I'm gonna do, this is the origin of the grid, 0, 0, and when we go further, that's the, I'm thinking where's the x and a y. So this is x. So when x grows, we go right, and when y grows, we go down. So this is 0, 0, and this is 5, 0, or whatever. This is 2, 1, stuff like that. So this is a forest or a 2D list, a nested list, and let's now find the element. Wait, so if we drop out, that's the y coordinate. If we drop out, that's the y coordinate. And the y coordinate, where is it? It's the number of rows, so it's the first dimension of this matrix, right? I think so. I'm trying to decide, is it a good idea to combine falling out of the forest and finding an element at a specific location? Am I gonna regret this? I am already regretting it because it's getting a bit complicated in my head. I'm gonna go for it. I have a feeling it'll pay off. So the number of lines is how deep our forest goes, and whenever we ask something where the y coordinate, so the vertical location, is bigger than our forest, we drop out. So we have no element at it. So if y exceeds the forest length, -1, probably. If we have a 2x2 grid, length is 2, and our y's are 0, 1. That's okay, but 2 and bigger. So if it's bigger or equal to how deep our forest is, then sorry. And otherwise, we just dig into the forest at this location to get the row, and then to get the column, we just find the element in the second dimension and return sum. So I'm using an option here to say, like, yeah, there is an element like in the first part of the grid or in the ever-growing horizontal part, but if we go too deep, so this is going to be our end condition. If you go too deep, then we return, like, there's nothing here. You're in the void. You're in deep space. Now I'm thinking, is there like a more elegant way of doing this? Probably there is. I think there's a list dot. All those try functions on the sequence modules, they all return options. So I think they're basically what we're trying to achieve here. Try item, does that take an index? That does take an index, and a list, and returns an option. I think this is literally what we're trying to do here. Am I going to refactor it? Let's not refactor it right now. Let's just see if our idea is working. So let's load everything into the REPL. Let's play around a bit with our element add function. And I'm already regretting that I didn't keep a test grid, but let's make this our test grid for this example. Let test forest. I'm just gonna have an example of a forest, and when we look up an element in this forest, let's just do 0, 0 first, like the origin. We would be expecting an empty space, the only empty space in the forest, and it's sum empty. Let's see. Yeah, so that works. Let's go line and a column deeper. So that should be one line and column deeper. Should be that one. And that's 3. Yeah. And let's try to go out of the forest, or no, go further than our initial input in the horizontal direction. So that is the y coordinate. So this is 0, 1, 2, 3. Let's go 3, and it should also be a tree. No, it's not. Interesting. Some tree, and saying none. So our y coordinate, yeah, of course, our y coordinate is, okay, stop. I'm getting confused. This is the second time already. Let's draw something. So we have our grid. Let's draw the test grid. So we have empty and then 3 trees. We have a grid. Why am I drawing a 3 by 3 when I'm doing a 2 by 2? This is better. And we have empty and 3 trees. Jesus, that's difficult to say this early in the morning. So this is what our grid looks like. X. This is X and this is Y. And we start at 0, 0, 1, 0, 0, 1, 1, 1. So the thing we were trying to look was this guy. So it's 0, 1, 2, 3, 0. That's the one we're trying to look for. So if this was totally wrong, it's 3, 0, and that should be a tree. Yeah. Okay, we haven't implemented this case yet. Yeah. I'm sorry. So this should be working, but we're just accessing the list here and we're not looping around. So this should be modulus. So modulus what? Modulus the width of the first part. So actually modulus this thing's length. So let's extract this into a variable. And now I'm confused again by the off by 1 potential in here. So let's just test the snot out of it. So this is working. If we go 1 back, so 0, 1, 2, it should be the empty one again. So now we're here again. No. 2. I'm saying things and I'm not typing them. I'm sorry for this. There we go. Let's see if everything's correct. Yeah. I'm gonna get that stuff out of there so that my test print, my test log is okay. So whenever I see this testing done without an error log in between, I know that all my tests are green basically when I'm doing REPL driven stuff. So I think accessing elements works, but the falling out of it, let's test that part. So whatever, like when we're looping around, but we drop out of it, 2, for example, we should find nothing. We should find empty space. Yeah, we do. Okay, I think that's good enough. We have a parsed forest and we can inspect what's at a location. We're hitting a tree or not. So what's next? Next is navigating through our forest, I think. First some coffee because this is getting wild. I'm playing Hyrule Warriors, by the way, so I'm back into Zelda. Anyhow, yeah, I was saying in the beginning when I was thinking about the algorithm that I didn't want to have the fixed number of iterations because maybe part 2 will have this going up again or something crazy like that. I would rather have like a stop condition, and the thing we're building now, actually the stop condition is in here because we keep going whenever we hit something until we hit empty space. So actually our element add, the thing I was struggling with a bit, like sometimes you return something, but if you fall out of it, you return nothing. This is going to be our stop condition as well. So we keep going, we keep iterating over in our forest, or we keep moving in our forest using that pattern provided until we hit none. So we're poof, fallen out of the forest, and then we know we stopped. So this is our stop condition. What do we need to do in every iteration? Well, it's basically we are at a location. We do a move, we check where we're at, if we hit a tree or not, and we just count. I think we count the number of trees we hit. That's more than enough for this puzzle. So how would I do this in C#? While hitting stuff, or no, while finding ourselves in the forest, we keep going until we drop out of it. In F#, we could do that as well, but I'm going for a more I would say idiomatic, but it's not really more idiomatic. It's more, I would like to use collection functions. And there's some functions in there that could help us with these kinds of puzzle. Let's go to a heavily used website of mine. It's not my website, but I use this website every time I work with F#. And it's called F# for Fun and Profit by Scott Larsen. I'm sorry if I mispronounced the name. But it's basically Wikipedia for F#. It's amazing. And he has posts on everything, from monads to collection functions, everything. If you have a question about F# and you find a link for F# for Fun and Profit, that's where it's at. That's where you have to be. But anyhow, he wrote a post on choosing between collection functions, and this goes over every type of collection F# has, like list, sec. We've been using it for a couple of days for the last parts of the puzzle, for the last puzzles. I'm sorry. But if you're interested in digging into the provided collection data types in F#, or the ones in the language itself, this is a great place to start learning. And there are some, so like there's chapters. So what do I want to do? And I kind of want to do, so aggregating or summarizing, that's almost what I want to do, but I want to do something until I hit a stop condition, basically. I know what I want to use, but I'm trying to see if I can find it by using this table of contents. Threading state through an iteration. Yeah, maybe this is where we'll get. So yeah, a fold is what most people already. A fold is what most people already have used when they enter a functional program, or when they have some experience with functional programming. But I'm looking for something else, because a fold is like you have a list and you have some kind of state generating function. Is that enough? No, because why can't we use a fold? You need the number of elements in a list is like the number of iterations your fold will use, and I'm explicitly trying not to do that. So fold is not what we need, but there's this thing with 2 letters more called unfold, and I'm not finding it through the table of contents. So let's go. Yeah, so it's creating a new collection of indefinite size. That's not really what we're trying to do, but in a way we are. So what am I trying to do? What's the algorithm I'm going to try to write? We have our initial position, we have the initial forest, and we have hit no trees. So this will be our starting state. And then we're just gonna unfold. So we're gonna create a collection, but the collection, it will be like every state. So every time we move, we have a new element in the generated collection. And this keeps generating states, so we keep generating moves until we drop out of the forest, and then the last element in this generated or this unfolded collection, that will be our end state. So let's look at the example quickly. So okay, say you have something that returns an option. Hey, we have something that returns an option. And then you can just use unfold to generate a list from a starting state. So in this example, what are we actually trying to do here? There's this function get input. We read a line from standard in. And if they don't enter anything, we say nope, no input, and otherwise we return state. And this is, yeah, this is interesting for us as well. So you don't just return, yeah, we need to look at the type basically. I'm sorry, I'm all over the place this morning. So what does unfold do? Unfold takes a generator function and a state. This is the initial state, and it returns a list of something, a list of t. And this generator function, this is where it gets interesting. So it's something that takes a state. So no, maybe let's bring this back to the example. Our generator will be the let's take another step kind of function. So our input will always be like the state, which would be where are we right now and how many trees have we hit already. And what will this function return? It's an element in the sequence that we're doing. So actually a new state, which will be, do we actually need end result, or can we just thread through and take the state? We need this t because the result type is a t. The result type is not a state. Now I'm confusing myself with this tuple thing. So I see this makes sense here. So they're generating a sequence of strings until they hit a certain number of lines, but we just need to keep generating. It'll work. It's a bit confusing, and I don't know why I'm gravitating towards unfold, but I'm gonna try it anyway. Ha! So let's call this let find number of trees on path out of. That's a very long name. So our forest is again the forest type we defined. I recently switched to QWERTY and I'm learning, so I'm sorry for this. Okay, so we have a forest and we need to find the number of trees on the path out. Am I happy with this thing? Let's not write a function. Let's just play around for a while. And this is where it's at. We want to unfold, so we need a generator and an initial state. And that's it. Initial state. Good question or a good point. Let's define our state. And I like to, whenever I'm doing unfolds or something, I like to define like a mini type that's like an accumulator or this state thing. Let's literally call it state. Why not? So what are we keeping track of? We have the forest, but I don't know if this needs to be an explicit part of the state because it won't change. It's like it's there. We have a map. Don't care. But what do we care about? It's our location. Where are we at? And that's, we've been using a tuple, a 2x2, or a tuple. Is a tuple like, does it have two elements? We're using an int and an int. There we go. And the other thing we need is how many trees have we hit, or are we going to keep our sequence of all the spaces we visited? Let's just do that, yeah. Visited is a space. Well, space is a weird name, but okay. So what's the state we're going to keep track of? Where are we? And which spaces have we visited? So these are sometimes empty, sometimes trees. And when we're done, we can count the number of trees in here. So this is our state, sure. Now we need to do the generator part. So generator is the thing that will take a step, and our initial state is something that starts at the start. Where's 0? Okay. And visited is like nothing. And our take step function, what does it have to take? A state, and it returns the next element in the sequence, and the state. So it takes a state and it returns whatever. I'm confused about that part right now, so I'm sorry. State, it has to return an option. Okay, so that the type signatures line up, so that's already, or the types line up, so this is already okay. Now you just need to noodle a bit on this part. So this thing will keep going until our takeStep function returns none. Basically, we need to call, where are we right now? So let's do that. Let element is element at, am I going to just I'm not taking the forest as input here. Let's ignore that for now. Let's just do let's ignore it. Let's not ignore it. Let's take the forest. I was writing a function first, but I didn't do it here. So let's do takeStep forest right here. Do we still have the forest? We don't. So let's parse this forest back again. There we go, and takeStep. This is partial application, by the way, so I'm just saying, like, make a new function with forest already filled in. So this will work. This will work. So this is a function that takes a state because we already passed in the forest, basically. So this argument is already filled in, and now every time unfold uses this to generate a new step, it'll just provide the state, and everything aligns. Cool. But we were looking at this function, so the takeStep function. First thing this needs to do is look at the forest. Was forest the first argument? Yes, it was. And see what's at state.location. Let's type this. We're going into maybe a type is not a bad idea territory here. So let's actually do this. F# has strong type inference, but sometimes it's not a bad idea to explicitly type your input arguments or your return types for that matter. But anyhow, we have potentially a space, and if we have an element, we can just move. Why am I doing location? We need to find a new location first. Let's do that. So what was the pattern again? Right 3 down 1. So new location is state.location. Let's extract that. Let new location is right 3 down 1. Right was x. Let's go back to our drawing to be sure. Right was x, yes. So new location is right plus 3, so x plus 3, and down, was it down 1? Where's my puzzle? Down 1, yes. So y plus 1. This is the new location. This is a location we are interested in. Now I'm thinking if we do the step first and then do the find the element, and when we drop out, we're not gonna have our final location. But that's not what we're looking for, so let's not worry about that. So we know where we are. And now we can use these fancy option.map or bind things. But let's not do that right now. Let's keep it simple and just do a pattern match. So if we find, let's first do it this way. If we find nothing, this means we have fallen out of the map. This means we're done. And we're done means when we're using unfold, this means return none. if we find something, we return a new or an updated state and t. Ah yeah, and then we can return a new location perfectly. So sorry, then we need to return an option. So this is now saying if we find an element, no, if we fall out of the map, so the element that returns none, then we're done. And if we do find something, we return some. So this means we keep generating a next state in the next iteration as well. And we go, or we're not generating states, I'm sorry, we're generating t's, and the t's in this case are ints by ints. So the unfold generates our list of positions basically, but we're not that much interested in the list of positions. We're interested in the state. So yeah, this is a bit weird, but I decided to go with unfold. Let's go with unfold. And I was saying we can use fancy option functions whenever you do stuff like this, like if it's a none, if it's a none, if it's a sum, do something. There's functions for that. So I think this is an option.map. Yeah, so this is something that takes a mapping function that just like of any type that maps something to something else, and it takes an option and returns an option. So this does the exact thing we're doing here. So let's use that in a second, but let's first actually do something. I'm looking at the other one. Yeah, this is more for monadic stuff. Let's forget you ever saw option.bind. So now we're not doing nothing. So we have the algorithm in place, but we're just saying, okay, and the next state is our current state, which is obviously incorrect. So let's calculate our new state. And I'm going to use something called with syntax. So that's basically when you have a immutable type. Is this the syntax? Yeah, I think this is the syntax. Types in F# are by whenever you define a record type or whatever, whenever you define a type, it's immutable by default. So the state thing, if you have an instance like this here, this initial instance, you can't just update it. Everything is read-only basically. And if you have to update it, you create basically a new version of it. And this is what you can easily do with this with syntax. So this is saying just take a copy of state basically, but have a different location property. So this is what we're going to use, but location is actually the new location, and visited is actually the original visited. Yeah, but add the element we're seeing right now to it. So we have a location and list of visitors, we update the location correct, and we say, okay, we visited this tree or this empty space. I think we are done. I think we are done. Let's just load this into the REPL. My keyboard makes a whole lot of noise, I noticed while looking at the previous videos. I'm sorry. Maybe I'll do something about it, maybe I won't. I like the way it feels, but it's terrible for video. Actually, we have our answer right here. Let end state. Let's just run that again. Are we in an infinite loop? We are in an infinite loop. Oh no. The worst scenario is happening. We are infinitely looping. We are infinitely looping because we are still not using our next state. I'm sorry. Okay, there we go. Debugging this is more interesting than I'm used to in like regular old C# stuff. There we go. We have this is a weird end location. No, 123. let's go back to our input. Oh yeah, x doesn't matter, but the y coordinate, it should be 324, right? Why is it 123? Why are we stopping? Oh no, there's 3 dots here. This means this is not the end of the story. Okay, so this is the list of all the states we generated, which is overkill. We only need the last one. So actually, let's do... Yeah, it doesn't make sense to do a sec or a... Does it make sense to do a sec instead and then take the last? Who knows? There we go. This is our end state. This is better. It's 322, is that? Yeah, that's more like it, because we were not taking the step out of the forest into our state. So this is the correct one. And now we just need to count the number of trees. End state. Visited. And we need to count the number of trees. And this was the list of spaces. So let's filter out the... is that a shorter syntax? Let's filter out the trees. So this should only return me trees are in there. That is correct. And let's see how many we have. $211. Hey ho, let's go and pray for success. There we go, correct answer. So this was a bit chaotic, I must admit. But yeah, you're experiencing this with me on the fly. It's pure chaos in my head as well. So I would probably give this some love and clean this up if this was an actual problem, and think about it a bit more before I dived right into it. But there we go, part 1. Let's take a look at part 2 quickly. What do we have to do? Time to check the rest of the slopes. There we go. There's not one slope, there's different slopes. Minimize the probability of sudden stop. Okay, determine the number of trees you would encounter if for each of the following slopes you start. So we need to do this experiment, like counting the trees we would hit for multiple slopes. And they all go down. Yeah, they all go down 1, except this one that goes down 2. Yeah, so I think don't rely on the fixed number of steps. It'll pay off. So we need to find the number of trees we hit for every slope, and then multiply them. Okay, that's just a detail. So we need to find the number of trees we hit for different slopes. My coffee is ice cold already. Great. Let me just copy paste this for part 2. So we need to run this experiment for more than one slope. Where's our slope at? This is our slope. Are we just gonna thread it in through state, or are we gonna provide a new slope here? Let's do it here. Slope. Let's also do a tuple. Let's take step first, and the slope for first example is 3, 1. There we go, and let's use slope. Let's use the values we get from slope. So now we parameterized our step taking with the slope. So when we run this, we should get the same results. which was 211. Let's see if that is still the case. Yeah, let's make this a bit bigger. It's still the case, cool. So it's still working, but the difference we have right now is we can provide a slope. So let's make a function that does this basically for a given slope. So let's call it run given a slope and a forest. Yeah, let's do run an experiment with a slope, and we do whatever we did. Yeah, so for a slope, do the experiment and return the number of trees we hit. This is exactly what this function is doing. And now we need to run. Now we need to run for all the slopes we've been given. So all the slopes we've been given, and do a map. So when we have the slope, just do run slope. There we go. And 3, 1 is not what we're doing. It has to be the slope, and 3, 1 is a slope. So I'm like pushing the variables up the stack. So first we had it hard coded, then we take in an argument, and now we provide it, and now we can run our run function for multiple slopes. What are the slopes? I'm just gonna copy paste them. No, I'm just gonna put them side by side. There we go. Come on, Windows, don't fail me. Give me screen state. Oh my god. Oh my god. Thank you. So 3, 1. That's the second one. First, then we need 1, 1. 3, 1. 5, 1. 7, 1. Come on, keyboard. And 1, 2. These are all the slopes, and we run our experiment for that slope. So this is basically this. And then we have the list of trees hit. Let's go. There we go. 211, that was the part 1. Yeah, so that's correct for the second one, and these are the hits for all the other ones, so let's just multiply them. By using reduce, because why not? Is this, yeah, that's correct. Hey, that's a big number. That can be correct. No. Oh? I'm confused. But okay, let's worry about that later. Let's first try to solve it. So these are the ints. If we multiply those, do we get a number that big? Yeah, that's what reduce does. I'm confused about the order. You know what? Let's pull up calc. Let's see this happen before our eyes. 67 times 211 times 77 times 89 times 37. Yes, that is a big number. So let's lift into big number space. What's the big number thing in F#? What are we hitting? Or basically this. Let's just see if we're correct first. Is this for all the slopes? Yes. So let's remove the commas. There we go. Let's feed it to the puzzle validator. There we go. So it's correct, but I'm not gonna clean up my code, but I'm gonna multiply these numbers as if it's the last thing I do. So for really, really big numbers, we need an int64. So let's first map these numbers to int64s, and let's multiply them There we go. 385 385 358. Yeah, that looks great. So it's a big number. Beware. That's it. Let's see. Let's look at our final code. What do I like? What don't I like? Do I like these nested for comprehensions? Yeah, why not? Element that. I think there's another way to do this without the evals, but this is clear. Take step. Yeah, sure. This thing I would not keep. I would do an option dot map. Yeah, let's see that in action actually. So whenever you pattern match on an option and you only do something in a sum case, you can achieve exactly the same thing using element option dot map. And this basically unpacks the option for you and does something in the case of sum. So this is literally what this piece of code would do. I thought. Oh yeah, and then you don't need to wrap it into an option yourself, because that's what option map does for you. So is it better? I don't know. Is it more concise? It definitely is. And that is about all I'm going to do for cleanup today, because it's Advent of Code. It's all about having fun and solving puzzles. I hope you enjoyed this trip down madness and chaos F# lane, and see you tomorrow.